Hi and welcome. I'm trying to learn electrical engineering, today energy and power, and after we've done it we're going to do leg injury prevention training, and if you participate in the leg injury prevention training, is it risk. Now we already had this in two parts, but we want to do our over it again. I'm trying to remember the formula. I think it doesn't make a difference because of multiplication. Energy equals power multiplied with time. Energy and power. We use electrical appliances at home to transfer energy from the main supply to heating, light, movement and sound. In 2 hours, an electric lamp uses twice as much energy as it uses in 1 hour. The power of that means it's gradual usage. The power of an electrical appliance tells us how much electrical energy is transferred in a second. I still feel uncomfortable. I don't remember, I think I mentioned it. I feel uncomfortable with the word appliance. I don't understand the word. I get it from the context, all these electrical appliances, but I don't understand the word. Power, P, is measured in watts. So the power is measured in watts, but obviously we learn later that it's also measured in kilowatts. Power is measured in watts, and 1 watt is 1 joule per second. Per second. Appliances used for heating have a higher rating than those used to produce light or sound. The amount of energy transferred from the mains appliance depends on the power rating of the appliance and the time for which it is switched on. The longer the lamp burns, the more energy it uses. Energy transferred from electricity is worked out by energy equals the power times the time. So the power which the toaster uses needs 800 watt times the time it is running. And that is the energy it has used, the toaster. E equals P times T, energy equals power multiplied with time. Energy E, is measured in joules. And the power is in watts and the time is in seconds. So if there's somewhere written the power is 800 watts, and someone is so kind and says us how many seconds it's running, we're going to calculate the joules something needs. Now get it, we just can convert hours into seconds and then we can... No, I don't know it. But it would work if we get joules and hours told, and we have to calculate the kilowatt or whatever. In kilowatt hours should be try to calculate out when we have the time in hours. I don't really understand what they mean if we have a time in hours or in seconds. It would make much more sense if we could calculate from one to the other. Example, a 300 watt electric pump is switched on for 1 minute. The energy used is 300 watts, as it needs, and we have it in watts, so we should calculate in joules. And what if we should calculate in kilowatt? That is my question. But we should just say patience. I think it's coming here. I think there's something written about it. Okay. If an electric pump has 300 watts, we should calculate the joules. It's running for 1 minute. 1 minute are 60 seconds, so we should calculate watt times the seconds. It has 300 watts and burns for 60 seconds, and these are 18,000 joules. That electric pump uses in that 1 minute 18,000 joules. And in the second example, we're having a kettle. Maybe that's a kettle. But I'm not sure. A kettle 2,200 kilowatt, no, 2,200 watt, or 2,000 kilowatt is used for 10 minutes. Now we have to calculate. It runs for 1/6 of an hour. We have it in 2.2 kilowatt, so we should use through hours. So we have to calculate the 10 minutes into hours. By the one previously we had to calculate the minutes into seconds. Now we have to do the minutes into hours. And it went at 10 divided by 60 hours to tell here. That is true, I think. Yes, 1/6 of the time. 10 divided by 60. So to get it into hours, we divide by 60. The minutes divided by 60. And when we're having 2.2 multiplied with The thing in minutes, 10 divided by 60, and these are 0.37. I'm wondering if I should show you that, what will be useful. I'm just not sure if it is useful if I show it. So 2.2 kilowatt for 10 minutes. And to get it into hours, we have to calculate the minutes divided by 60. And the first number done when multiplied with the result in minutes, and this is 0.37. In the next part, we will continue here with something to do with joule and kilowatt. So in the next part, we will continue. Now we're going to do the electrical engineering. If you register for electrical engineering, you can go directly to the next part, where we will continue with this joules and watt calculating. Here we will do leg injury prevention training. If you participate in leg injury prevention training, that's the always. First exercise. One leg with flexible in the air, moving in the front and to the side. Now I can read it on. But not for the next part. I've seen it. Now we had previously the thing with the generator. And generators have strong magnets in them. And the stronger the magnet, the more voltage is done. And voltage is the electricity. And the more turns the wire has of a coil, whatever the coil and the wire are, that also makes more voltage. And also the faster the magnet rotates inside of this fixed wire, the more voltage is produced. And putting an iron core inside of a wire helps also to produce more voltage. Next exercise, 1/4 of a flex foot in front and back. The voltage is only induced when there is movement of a magnet or coil. If that thing is standing around, nothing happens. The direction of the voltage is reversed when the movement is reversed. Now, that means that we're keeping our eyes and ears open, the other foot, to look if at some place, while we are learning electrical engineering, we find out how voltage can have a direction. And the next exercise. We bring one leg up, breathe in, out the leg to the side, again in, out into the middle, and down. And the other leg in, up, breathe in, out to the side, breathe again in, out to the middle, down. The other leg up, breathe in, out to the side, breathe again in, out into the middle, and down. And again the leg up, breathe in, out to the side, breathe again in, out into the middle, and down. And the next exercise, we're bringing one leg up, and we're pressing from the side against the knee. Riding with the leg, flex foot, even the lips taller, back, a little bend in the elbow. Now, knee presses up to the side. And the other leg up. Right angle with the leg, flex foot, even lips taller, back, and pressing on the inside. Little bend in the elbow. Now the knee presses up and to the side. And the next exercise, one hand on tummy, one on lower back, and the lifting one leg straight up. If a quad muscle cramps, I'll bring the leg up and point the foot up. Bring your leg high up and try to bring it high up. Control the hands so you don't fall back. And bring the leg up and point the foot out. And the other leg up. Flex foot, try to bring the leg high up. and longer, and we're doing the pipette. One leg points with the toes to the outside, the other one with the heel into the ground. We're just going to put it off the ground, placing it again on the ground. I'm a bit wondering about the names of physics. I think that is named after a person. Power. Power is an English word. Completely normal English word. Joules, I don't know where it comes from. Maybe it's from a person. Energy is a completely normal word. Kilowatt hours. The other leg. Kilo is, I think, Greek origin. Watt könnte again a person sein, and hours is again a completely normal word. Did we have a generator? It maybe has an origin somewhere in the ancient world, but it's a normal English word, I think. I don't think it relates with physics. Dynamos, I don't know. Electromagnetic induction. Where does the word electro come from? Turbines, coal-fired. Okay, these are names for the things itself, for objects. I'm just wondering about the names because I notice they're different than to other signs. And I'm wondering if there might be the difficulty for some people to understand physics. Power, watts, joules. These are not names people can understand something under, and they're used for other things. These are not Latin-based complex words like chemistry or biology. I'm wondering about the words. We're going to look for more words, and maybe keep it back in mind. If maybe the choice of the words, or the words with which the physics terms are used, maybe just the words itself are proper for some people to understand physics. The next exercise, you're going to be doing the step first, leg up and down, up and down. And the other leg up and down, up, down, up, down, up and down. Now hold. If you like, you can do the stem step. We're having the arm in and the leg in and out. That is the horse. In with the leg and out. Don't pick yourself. So up and out, up and out. And the next exercise. And again, we knee in and out, in, out. You can take a break if you like to. Now we're going to do the camel. You can still do the horse or take a break. Knee in and out, and we're going up and down while we're doing it with the leg. And last time. Now with the other leg. In, out. And now the last exercise, you can take a break or do the horse or camel step. We are having our leg up and we're swinging it back. Flex foot. The upper part of the body comes in the normal down. Which the leg comes up. Try to have a tall standing leg. And try not to fall in the abdomen. And the last one. Now with the other leg. And last two. And now we're closing. They're moving in. And out. Again in. And out. And last round, breathe in. Out. Breathe in, close the legs. And out. This was the leg intervention training. I thank you very much and until next time.